Hello, in this video we're going to introduce Chapter 5 by talking about Section 5.1, the graphs of sine and cosine functions. As a little introduction, these are some topics that the graphs of sine and cosine functions are good for describing. So white light, such as the light from the sun, is not actually white at all. Instead, it is a composition of all the colors of the rainbow formed in waves. The individual colors can be seen only when white light passes through an optical prism that separates the waves according to their wavelengths to form a rainbow. Light waves can be represented graphically by the sine or the cosine function. In the previous chapter, we examined trig functions such as the sine and the cosine function. We also talked about tangent, cotangent, secant, and cosecant. In this section, we're going to be focusing specifically on sine and cosine and interpreting and creating their graphs. To generate the graph of a sine and cosine function, we can use the unit circle. In our coordinate plane, when we are graphing trig functions, we use our vertical axis to describe the ratio. So our graph will be bounded between 1 and -1, since the sine and cosine functions are bounded between those units. And our horizontal axis will be our degrees or our radians. So what this picture is describing for us is that if I have a 30-degree or a pi/6 radian angle, it would be my y value for my sine function. So the y value would put a point at the intersection of that y value and the input of pi/6. So I would have a point right here on my graph. If I look up to a value of pi/4 radians or 45 degrees, my y value vertically is about here on my unit circle and would map over to about here as a coordinate for an input of pi/4. Going up to my angle of pi/3, my y value would be approximately here, and over at the angle pi/3 for that input, I would have a point there, and then at pi/2, I would have a point at 1, because on my unit circle, that y value at pi/2 is 1. So we are just looking around the degrees on my unit circle, finding the y value of that point, and then placing that point at the coordinate that has an input of that angle. So starting at 0, 0, because at 0 radians or 0 degrees, my y value is 0. Starting at the origin, my graph increases in a curve. To find these remaining points, we're going to go ahead and refer to our chart. So we know that the x value, a degree of 0, gives us a sine of 0 and a cosine of 1. That's this point here on my unit circle. Moving around my circle at 30 degrees or pi/6 radians, I have a sine value of 1/2 and a cosine value or an x value of square root of 3/2. At pi/4, I've got square root 2/2 for x and y. And then at pi/3 or 60 degrees, I have 1/2 and square root of 3/2. Excuse me, I switched those. My sine value is square root of 3/2, and my cosine is 1/2. At pi/2, my sine or my y value is 1, and my cosine is 0. Continuing around my circle at 2 pi/3, I'm going to have a reflection of my pi/3, and it would be square root 3/2, and my cosine would be 1/2. At 3 pi/4, I would have a reflection of my pi/4, so square root 2/2 for both x and y. And at 5 pi/6, I would have a reflection of my pi/6, which would be a 1/2 for sine and a square root 3/2 for cosine. Now, because all of those angles are in this second quadrant, after my pi/2 up until my pi, all of these should have negative x values. Since we're above the x-axis, my y's will still be positive. Once I hit pi, which is here, I have a 0 value for my sine, -1 for my cosine. Going another pi/6, I have a reference angle of pi over 6, which means that 7 pi over 6 would also be 1/2 square root of 3 over 2. Since both of my sine and cosine are negative because we are below the x-axis and to the left of the y-axis, both my sine and cosine here need to have values that are negative. 5 pi over 4 is going to have a reference angle of pi over 4, so I've got negative rad 2 over 2 for both values. 4 pi over 3 has a reference angle of pi over 3, so negative square root 3 over 2 and 1/2. And we can complete the rest of the chart just using our reference angles. So plotting all of these points, what we're going to see is that 2 pi over 3 has the same y value as pi over 3. So 2 pi over 3 will have that same y value as pi over 3, which means that I have a point in the same vertical position. 3 pi over 4 has the same y value as pi over 4, so I have a point in the same vertical position at 3 pi over 4. 5 pi over 6 maps over to pi over 6, so I have a point in that same vertical position, and pi and 0 have the same y value of 0. So this graph increases in a slight curve and then decreases in that same curve. Now, as we proceed through the second interval of our graph, we've got values that are repeated, but now they are all negative for my y values. So the same curve will repeat on the interval of a pi, but all of those y values are negative, so my graph is going to look more or less like this. So starting at 0 and ending at 2 pi, I've got a positive interval from 0 to pi where all of my y values are positive, and we can see that on our unit circle. Around this top half of the unit circle from 0 to pi, all of my y values are positive. Once I hit pi and continue around to 2 pi, all of those y values are now below the x-axis, so they are negative. So from pi to 2 pi, all of my y values are negative. Now, if we were to continue going around, if I went around the circle to 2 pi, that completes one cycle of my graph. And if I continue around after that 2 pi rotation, I'm going to start repeating my graph. So this graph completes one cycle in an interval of 2 pi, and then after that, we're just going to start repeating that cycle again. We call that cycle, that distance that it takes to repeat, the period of the function. And that's something that we're going to come across again later in this section. We can repeat this for our cosine function. Our cosine function will look very similar. We can take all of those cosine values and plot them on our graph. And what we are going to get is a graph that looks something like this. Instead of starting at 0 and crossing through at pi, on the y-axis we start at 1, cross through at pi over 2, and then we will cross through again at 3 pi over 2, and complete the cycle again at pi. And the reason our graph looks like this is because at 0 I have an x value of 1 and a y value of 0, but at 0 degrees, so 0 is my degrees, my y value will be 1. In this graph, the y value is referring to the value of the cosine function. So when we are graphing the trigonomic functions, the y value is referring to the value of the function. So even though cosine is in our x position, that is on the unit circle. But when we go to graph the trig function, y is then the value of cosine. So at 0 degrees, cosine takes a value of 1. At pi over 6 degrees, cosine is going to have a value of square root 3 over 2. So I'm looking at pi over 6 on my unit circle, and cosine is square root 3 over 2. Sine is 1/2. So at this pi over 6, or 30 degrees, my cosine value is square root 3 over 2. So the value of my function for cosine is square root 3 over 2, which puts us at that y value. Looking at the square root of 2 over 2, For cosine, that occurs at my pi over 4. So the y value would be rad 2 over 2, and at pi over 3 or 60 degrees, my cosine value is 1/2, and sine is square root 3 over 2. And we can see that this y value is 1/2 because it's in the middle of 0 and 1. So the cosine function takes a value of 1/2 at the angle of pi over 3. So using our unit circle and plotting those points, the angles and the cosines, we can generate our graph of the cosine function. We have a few specific characteristics for our sine and cosine function. I briefly mentioned that these functions are periodic because they repeat after 2 pi. The domain of each function is all real numbers because there is no end horizontally to what values these functions can take. This would be on our unit circle. It would be equivalent to spinning around the circle repeatedly until we stop at a particular angle. So moving horizontally, while 2 pi completes one rotation, I can move beyond 2 pi and complete multiple rotations. I can spin around as many times as I want, so I can move infinitely in our horizontal direction. Now vertically, however, our graph is bounded by 1 and -1 because our unit circle is bounded by 1 and -1. Unless we multiply the graph by a value that will increase that interval, the functions themselves will only have outputs of 1 and -1. The graph of sine we talked about is an odd function. Because it is odd, it is symmetric about the origin. So if I sketch out my function, it's going to look something like this. And on the left, if I continue this graph, it will go down to the left, and it will mirror the top right quadrant, or the first quadrant, as an image that has been rotated around the origin. Our cosine function, we said, was even, and for that reason, it is symmetric about the y-axis. So if I fold this graph on the y-axis, all of this graph on the right would stamp over to give you the graph of the cosine on the left of your y-axis. In standard position, our midline for both sine and cosine is y equals 0. A midline is just the center of your graph, speaking vertically. If I sketch out my midline for this graph, it is going to be on my x-axis. And the reason it's on my x-axis is because I would go 1 unit to get to the peak of my hill and 1 unit to get to the base of my valleys. So that midline is right in the middle of your graph, in between your hills and your valleys. The amplitude is what we refer to for the distance from that midline to the peak or the valley of your graph. So the amplitude for sine and cosine with no other transformations is just 1. It is 1 unit from the midline to the peak and 1 unit from your midline to your valleys. For sine, we have a picture of our sine graph as it is symmetric about the origin. Same thing in regards to our amplitude. It is still 1. Our midline is still on that x-axis. So the only difference here is that our sine function is symmetric about the origin because it's odd, while cosine is symmetric about the y-axis. All other features are going to remain the same for sine and cosine. So to find our midline, what we are looking for is the graph that sections off exactly the center between the peak of your mountains and the base of your valleys. So if I look at my peak, it is at 1 and my valley is at -5, which means that right in the middle would be a y value of -2. So my midline here is y equals -2. It is an equation because it is a line. Go ahead and take a sec to check out this graph and see if you can determine the midline. Feel free to pause the video if you need to. In this graph, since our peak is at -5 and our valley is at -1, my midline is going to occur at +2. So y is equal to +2 gives me the midline of this graph. That concludes part 1 of section 5.1. I'll continue in our next video. Thanks for watching.